Okay, I think I can start. Let me check. Did you check the Zoom, like if people can hear us? Okay, sounds good. Perfect. My name is Emrah Tıraş. I'm an associate professor in physics at Erciyes University, and also I'm vice dean of research at the university. I'm also affiliated with the University of Iowa. I have an office over there too. I have an adjunct faculty position over there. I would like to start thanking to the organizing committee actually for organizing this school and inviting me as well. And also, I just want to check the audience, like the spectrum of the audience actually. How many of you guys are doing postdoc? Okay, perfect, great. And how many of you guys are doing PhD or master at the graduate school? Okay, most of you guys. Okay, perfect. And how many of you guys are from outside of Turkey? International. Okay, perfect. That's good. Today I'm going to talk about neutrinos, nature's ghost particles, elusive particles, actually. And also, I'm just going to mention, like why we call them the ghost particles. But of course, I just need to start with the atomic physics, actually. So the atomic physics studied, and also, of course, like studies the atom as an isolated system, focusing on the nucleus and also its surrounding electrons as well. And then in the late 19th century, actually, with the discovery of radioactivity, nuclear physics kind of like came out, and it investigated the atomic nucleus, electrons, their interactions, the nuclear level, of course, and also it focused on the nuclear energy, nuclear medicine, nuclear radioactivity as well. But later on, the particle physics, which is exploring the subatomic particles of the universe and also the interactions actually with the main forces under mostly the standard model. Then neutrino physics, which is a kind of like subfield of the particle physics, we mostly focus on the neutrinos and their interactions. And today I'm going to talk about the neutrino flavors and also the neutrino detectors, neutrino energy spectrum, their sources and how they interact as well. But these are when we look at the standard model of particle physics, actually, we have four main forces. And most of you guys know the strong interaction, electromagnetic interaction, gravitational weak interaction. And then we have the leptons and quarks. And I also put the sizes of them here because after the quantum mechanics and also the special relativity, the particle physics is a kind of in between, if you want to study the particle physics, the interactions of the subatomic particles, so then you need to study quantum mechanics, special relativity. But at the same time, when you go to the neutrino physics, then you need to focus more on the weak interacting particles or the weak interactions mostly. Because when we say the particle physics, if you just put the gravitational interaction, outside of the other, fundamental forces, and then if you just put the three forces together, the strong, weak, or the electromagnetic interactions, then we study all three of them to be able to study particle interactions under the particle physics, of course. But then when we come to the neutrino physics, and we focus on mostly the weak interaction, and I'm going to focus on these today. In 1930, Pauli, and you can also see here, actually, we have the beta minus and beta plus, and how we actually can get the neutrino from the neutron beta minus decay or the beta plus proton decay. So you can just see a kind of, the Pauli said that I have predicted something which shall never be detected experimentally. But whoever said this, after a couple tens of years, and sometimes a little longer, actually, they made a big mistake, because 26 years after Pauli said this, the first neutrino, the first flavor of the neutrino, electron neutrino, was discovered in 1956 through the Cohen-Reines experiment in the US. And in 1962, just 6 years after that one, The muon neutrino was discovered at Brookhaven National Lab in the US. This is really important. And also in 2000, actually, the donut experiment at Fermilab achieved the discovery of the tau neutrino. Today, I'm going to focus on Fermilab, but also now, actually, you can kind of like understand why the US has been investing on neutrinos, because it's so important. All three flavors of the neutrinos experimentally detected were, discovered by experiments, collaborations in the US, actually. Of course, we have international collaborators as well in those collaborations experiments, but then the experiments, the detectors actually were in the US. We have three leptons, electron, neutrino, electron, muon, and tau, and then we have the cousin, a kind of like counterparts of each flavor, a kind of like electron neutrino for the electron, and then muon neutrino for the muon, and then we have the tau, and then tau neutrino, actually. And is there any other neutrinos? Of course, like there are so many questions. I'm gonna talk about them in my following slides, actually. So the neutrino oscillations, so which is really interesting, that also the first experimental investment, I can say, or a kind of, like the first experimental result beyond the standard model, because standard model tells us that neutrinos shouldn't have any mass. Okay, I mean, they don't have any charge, but they shouldn't have also any mass. But then in 1998, by the Super Kamiokande experiment in Japan, through the atmospheric neutrinos, it was detected that the neutrinos coming from the atmosphere is not the same what they detected, actually. So they are different flavors. We call them the flavor change, actually. So, for example, if we have electron neutrinos coming from the reactors and then they change their flavor when they move away from the reactor, actually, from their source. So we call this the neutrino oscillation. And then in 2001, by SNO, like Sudbury Neutrino Observatory in Canada, through solar neutrino measurements, actually, they also discovered the neutrino oscillations. So this tells us if neutrinos change their flavors from one flavor to other. So for muon neutrinos are a kind of like changing their flavor to the electron neutrino, and electron neutrinos are changing their flavor to the another type. So then they should have a mass. So, but standard model actually in the model itself tells us that neutrinos shouldn't have any mass. But this is the first experimental evidence and experimental result beyond the standard model studies, actually. So then the patch studies actually started on the standard model. And we have now actually so many models which are kind of like patching, adding to the standard model to be able to explain the nature of the neutrinos. And with this discovery, actually, the neutrino oscillation discovery in 2015, Takaaki Kajita from Japan and also Art McDonald from Canada, actually, they were awarded with the Nobel Prize in Physics. And I met with Art McDonald at Fermilab, and when I was a postdoc actually at Fermilab, he was visiting frequently, and I met with him, but I have never met with Takaaki Kajita. Why neutrinos matter? We have a couple of key properties. By the way, if you are okay, I just need to take my jacket off. It's getting a little bit hot. Okay, sorry. Okay. So why neutrinos matter? I mean, why are they important, actually? The first thing is they are the most abundant massive particles in universe. Photons are the most abundant particles in the universe, but they don't have any mass. But when we, focus on their mass, actually, they are the most abundant massive particles in the universe. They are, as far as we know, and they are the most weakly interacting and penetrating particles. So this gives us, a really good option to be able to study their origins, actually. Like if you want to study solar neutrinos, for example, and what's going on in the sun through nuclear fusion, so then these neutrinos coming from the sun, they don't interact much, actually. So then they just bring us the information a lot from the sun. Even you have a lead shield, 1 light year thick, which is almost 9.5 trillion kilometers. Half of the neutrinos from the source, after that thick lead, actually can be stopped. So then 50% of them still can come through your detectors. If you are able to detect them, then they're just going to bring a lot of messages actually from their sources and what's going on, kind of like what is the physics, in the sun through the nuclear fusion, etc. actually. And also they have the smallest known masses, more than 1 million times lighter than the electron mass, actually. Because recently Catherine experiment in Germany have been a kind of like trying to set, and we have a couple more experiments, they are trying to set a really good threshold, like the limits, actually, the upper limits for the neutrino masses, and they are less than 0.01 electron volt, actually, each of them. But do we know the mass of each neutrino? No, we don't know yet. So that's why we have so many experiments in the world today. They are focusing on the neutrinos because we would like to understand the mass of each neutrino. We would like to understand their oscillation parameters, etc. actually. They are electrically neutral. Their mass generation mechanism may differ from that all other known subatomic particles. I mean, as far as we know, actually the Higgs field interaction is a kind of like defining the mass of the subatomic particles, but the neutrinos may not be same, actually. We have a couple different theoretical models now, which is a kind of like trying to explain the mass of neutrinos, how they get their mass, because they are beyond the standard model, actually. And so then also it is a kind of like really good particles to be able to study the physics beyond the standard model. So that's really good. Yes, absolutely. No, I mean, mass eigenstates are different. I'm just going to mention about that one too. Yeah, definitely. Thank you for the question. Why neutrinos are important? They are also among the least understood particles within the standard model, because at CERN, at Fermilab, we collide, like high energetic protons, proton, antiproton, electron, positron, actually, the lab experiment in the past. And so we understand a kind of like how they interact within the electromagnetic interaction or hadronic interaction, all of those, like the hadronic particles, the mesons, pions, and we understand them and we know a lot about them, actually. But then the neutrinos, we know, we know the least information among those particles. Again, it's just going to give us a perfect start point for the exploring the physics beyond the standard model, and also that may help us understand some of the major open questions in physics, in particle physics or in neutrino physics. What are those questions? Why are neutrinos so light? Are neutrinos their own antiparticles? That's possible. So then if they are the Dirac type, it's not really possible. But then if they are the Majorana type, actually, with the seesaw mechanism, they might have their own antiparticles. Do neutrinos violate charge parity symmetry? We have so many studies actually have been focusing on this. And also the PMNS matrix, which I'm going to explain in one of my next slides, also is helping us to understand the charge parity, the charge parity parameters by using like several different experiments for the oscillation. Is the neutrino mass hierarchy normal or inverted? I'm going to mention this. I mean, how can it be normal or inverted? Are there only 3 flavors of neutrinos, or do we have sterile neutrinos, for example? And recently, Microboon experiments with their data at Fermilab just made an announcement that they collected, like 10 years of data, and then they analyzed the data, and then they published the results, and then told us they don't see anything beyond the 3 flavors, electron, muon, and tau neutrinos. So then they said in their data, they don't have any sterile neutrinos, actually. But does it mean we don't have the fourth type of neutrino or the fourth flavor of neutrino? No, of course. I mean, we should have higher energy and also, higher massive experiments, and then we will see if we have any other types of neutrinos. And also, is there a matter-antimatter asymmetry in neutrino oscillations? How we check this? We check by using the neutrino oscillation experiments. We can just send the neutrino beam versus anti-neutrino beam. Actually, we have three flavors. One experiment is just studying the electron neutrinos, and another is studying the electron anti-neutrinos, actually. One of them is studying the muon neutrinos, another is studying the muon anti-neutrinos, or one of the experiments I have been in part of NOVA experiment at Fermilab. So we have been taking data for almost like 7-8 years now. And half of the data is the muon neutrino data, half of the data is the anti-muon neutrino data, actually. So then we should be able to compare, like if there is any asymmetry or the symmetry actually in between the neutrino versus the anti-neutrino oscillation or the experimental results. And when it comes to the neutrino mass, and as your friend asked, like the mass of each this neutrino flavor, electron neutrino, muon neutrino, or the tau neutrino, is defined by this PMNS matrix. And then we have three eigenstates, actually. I'm not going to go in deep, like the mathematically for the matrix calculations, but I'm just going to mention that what we see in this matrix, actually, one of them is the oscillation, like the parameters. For example, the delta CP is a kind of like the charge parity, like delta function, to be able to understand what, like how these neutrino flavors oscillate to another types, actually. And also we have three eigenstates, nu1, nu2, and nu3, and each neutrino flavor is a kind of like the function or through these metrics, of course, calculation of these, like the three eigenstates, nu1, nu2, and nu3. And as for the mass, by using the experimental data from neutrino oscillation experiments, we are able to calculate experimentally delta m square between these flavors. So for example, NOVA experiments, the near detector at Fermilab, the far detector in Minnesota, it's almost like 800 kilometers away, as far as I remember. I need to check the number, of course. We have near detector, far detector, and then it's a controlled experiment, actually, because we accelerate protons, generate and produce the neutrinos, and then hit the near detector and far detector at the same time, of course. And then we see how many muon neutrinos we have at the near detector at Fermilab in Illinois, and how many muon neutrinos or the electron neutrinos we see at the far detector in Minnesota, actually, almost 800 kilometers away. So then we can calculate delta m square, actually, in between the muon neutrino to electron neutrino oscillation. But we don't know when it comes to the eigenstates, actually, nu1, nu2, and nu3, actually, if nu1 is the nu1 and nu2, actually, we know experimentally delta m 2-1 square, actually. They are close to each other, but we don't know if these two are higher than the nu3, actually, or if nu3 actually, like higher than these two, actually. So then when we look at see here, there you go. So when you look at these eigenstates, actually here, we know, we are able to measure these now, okay? So we have a couple of experiments actually have been measuring this. And then nu1 and nu3, and then we have nu3 here. If this is going to be, this is the mass. So then if this is the lightest, or if nu3 is the lightest, so then it is so then if you look at the, like nu1, nu2, nu3, or nu3, nu1, nu2, actually. So those are, of course, we have different models for this, but then we need the experimental, investigations or the discovery to be able to say that, like it's either normal hierarchy mass or the inverted hierarchy mass, actually. So this is one of the biggest questions in neutrino physics, of course. Okay, so here, what I also, as I said, the neutrinos, they are interacting weakly. And I said, even we put a lead of material, 1 light year almost, and half of them actually are not interacting, half of them can pass. But then how we detect them? They're also weakly interacting with our detectors. I mean, we see only a couple of them. But then luckily, it's a really good thing for us. The electron neutrinos, when they interact, we have the electrons actually coming out from that interaction. If the muon neutrinos are interacting, we have the muons are coming out from that interaction. If tau neutrinos are interacting with the matter particles, then we have the tau neutrino are coming out from that interaction actually. So that's really good for us because we focus on those 3 leptons. And studying tau is so hard because it decays so quickly. Then you need a perfect and high resolution, high timing resolution detectors. But then we can mostly study the electron or the muons, and also we can study them at a real high, the high efficiency or the high resolution, in the high resolution detectors with the high efficiency. And also, we have 2 different interactions for these. Either we have the charge current interactions that neutrinos interact. Either we have, as you know, the charge, the force carrier particles of the weak interaction, W plus minus or the Z bosons, right? And then if they are interacting with the W plus or minus, it's called the charge current interaction. If they are interacting through the Z boson, which is a neutral current interaction, actually, we have 2 types. Also, we kind of not only understand them from the theory, but also we have so many experimental results actually coming from the atmospheric neutrinos, reactor neutrinos, or the accelerator neutrino studies, I can say. When we look at this is really interesting because when we look at the neutrino energy versus the cross section, it's a really wide spectrum. So there's no single experiment you can study all of the neutrinos. I mean, we still have the neutrinos coming from the Big Bang. We have the neutrinos coming from the terrestrial reactor neutrinos, supernovae, or the atmospheric neutrinos. We have the accelerator neutrinos in the mostly, the mega electron volt to giga electron volt level now. But in the future, we might have some in the tera electron level, but we don't, we don't have many now. And we have the galactic or the extragalactic neutrinos. And then the peak for the extragalactic neutrinos. And as you can see, when the energy of the neutrinos are increasing, okay, because it's really tiny energy when we compare with the high energy physics actually. But then here actually, if you just focus on the galactic or the extragalactic, their cross section is really increasing a lot. So then, which means you can see them or able to detect them a lot easier than the other lower energy neutrinos, of course. So for example, the solar neutrinos, they are high energy neutrinos produced as a result of nuclear fusion reactions in the sun and other stars. They are emitted isotropically from the sun. If you look at the per square centimeter per second on the surface of the Earth, which is facing to the sun, we can see about 6.5 times 10 to the 10 neutrinos per centimeter square per second actually on the Earth. So which means that trillions of them actually are passing through in every, centimeter square area on the Earth. And their average energy is about 0.53 MeV, mega electron volts. And how we produce the neutrinos on Earth, we have a couple of them. One of them is the nuclear reactors. From the nuclear fission, we can see the electron antineutrinos, particle accelerators, Fermilab, CERN, J-Park in Japan. So then we can see high and intense neutrino beams are generated through the proton accelerators hitting to the targets like the carbon or the beryllium targets. And the geoneutrinos coming mostly from the Earth's interior due to the, radioactive decays of uranium, thorium, potassium, etc. actually. And then the atmospheric neutrinos are produced when cosmic rays interact with the nuclei in the Earth's atmosphere. Of course, some of them we don't really accept as a, like the human-made sources, because they are natural sources, like the atmospheric neutrinos coming from the interactions from the cosmic muons on the atmosphere. And then for example, geoneutrinos actually are coming from the radioactive decays of the uranium, thorium in the mantle of the Earth itself. But then when we look at homemade, I mean, usually we call them the human-made or the homemade. And then these are the reactor neutrinos. I mean, if you just build a reactor and then the nuclear fission, then you can see some neutrinos, and we should be able to detect them. And then we have the accelerator neutrinos. Again, CERN, Fermilab, JPark. I mean, we can accelerate the protons or the other subatomic particles to be able to produce neutrino beam, actually. And I'm going to mention on this later. So, as I said, we don't have a single detector to be able to study this energy spectrum of the neutrinos. So in the world today, and some of them are not here on the list, but most of them are here. And of course, we have new experiments are coming. We have different sizes, different geometries, and different specifications of these detectors. Some of them are the water Cherenkov detectors. Some of them are the liquid scintillator detectors, for example. But then the most important thing to be able to study the neutrino is the massive, huge detectors. Because if you increase the size and also the mass of the interacting, like the medium or the environment, so then you can detect more neutrinos because they are weakly interacting particles. The CERN is one of the neutrino, producers, and they produce neutrino beam and send to the Gran Sasso in Italy. So the OPERA experiment actually till 2012, it was run, but still, I mean, they took the data, but still they are publishing the results as microboon at Fermilab, for example. Why? Because, I mean, they are still analyzing the data. We have lots of data, actually, almost a petabyte. And then they are still analyzing the data, but it was stopped. And now the liquid argon detector of Gran Sasso was shipped to Fermilab. Now we have a short baseline neutrino experiment at Fermilab, actually, which is using the same detector what they used in Italy at Gran Sasso, actually. And how I studied, focusing on neutrinos, I was at CERN. I did my master and PhD through the University of Iowa, but at CERN, I 60-70% of my time actually was on the detector R&D, I can say, but 30-40% of my time was on the physics analysis. And then I studied the Majorana neutrinos coming from the proton-proton interactions actually at the TeV level. So that was part of my PhD thesis in 2015-16. That's how I was really interested in the neutrinos. Then I moved to Fermilab as a postdoc for neutrino experiments, and NOVA, and then I spent a couple of years on the neutrino experiments. At Fermilab, this is really important because why we focus on the accelerator neutrinos, and my research group also focus on the accelerator neutrinos, and the energy range is controllable. So if you increase the energy of the accelerator, the booster actually, for example, Fermilab main accelerator, main injector has 120 GeV protons, which is targeting to beryllium and carbons at two different energy levels. One of them at the 1.2 GeV, one of them at 700 MeV. We have two different beam lines, actually, as you can just see here. So one of them is this one, which is 1.2 GeV. Another is this one, the NA experiment. And then we have so many experiments on the beam here. We have so many experiments on the beam here. This is the third, this is the muon experiments, actually. But then we are, Fermilab actually is building a third beamline for the neutrinos, which is going to be the highest energy and highest intensity neutrino beamline for the Dune experiment. I'm going to talk about that one. And also how we, produce the neutrinos. I'm just going to do this. As you can see here, 120 GeV protons are targeting to do, different targets. As I said, mostly carbon and beryllium targets we use. And then the pions actually are generated. And we have a decay pipe where actually we let pions to decay to muons and the neutrinos. And then we have the absorbers here Those are mostly the concrete or the lead or the stainless steel materials actually, then you can stop the muons. But as you can see here, the neutrinos are continue their way to your detectors. So then on the road of the neutrinos, like on the beam road actually, so you can just build as many neutrino detectors as possible as long as you have a budget. So because they just continue their way, maybe you see a really small fraction of the neutrinos in your detector, and then the rest of them continue their way actually. Okay. So then the Fermilab, I'm just gonna mention about the Fermilab because it is one of the national labs in the world today, which is mostly focused on the neutrinos after they shut down the Tevatron. So this is one of the 17 national labs in the US under the Department of Energy. It is the second largest particle accelerator laboratory in the world after CERN, and established in 1969. But of course, it was colliding proton antiprotons by using the Tevatron accelerator until 2010. Because I mean, it was the LHC, Large Hadron Collider at CERN, started to run in 2008, and then at that time, actually, the President Obama decided to shut down Tevatron and focus on the LHC. Actually, that's why we have four main experiments at CERN, as you know, like we have the CMS, Atlas, LHCb, and also ALICE experiments. The almost 70% of the collaborators, scientists of CERN, CMS experiment are from the US, because they mostly focus on from Fermilab Tevatron to the LHC, Large Hadron Collider, CMS experiment at that time. What are the major discoveries at Fermilab? Discovery of the Higgs boson, they helped, of course. The discovery of the Higgs boson from CMS and Atlas experiments, and it got the Nobel Prize in 2013, as far as you know. But then almost 300 scientists actually from Fermilab have been focusing on and then studying that at that time. Discovery of the top quark, discovery of the bottom quark, and experimental discovery of the tau neutrino. That's why the US actually has been investing, like kind of putting so much money in the neutrino studies, because they would like to get the second, so for example, they want to be a kind of, like they want to achieve and say that they are the ones, they are continuing their discoveries like on top of their like 3 neutrino flavored discoveries. So that's what they want to do. And also the observation of the direct charge parity violation in Keon, and then the dark energy confirmation of one of their experiments actually. Of course, we have so many experiments. I'm just going to mention about, like, I think I have almost 30 minutes left. And I'm just going to mention quickly about what experiments we are collaborating with. And also, now on, I'm going to focus on the detector types, actually. How, like what kind of detectors, what kind of geometries actually we have for the neutrino detection. My research group, RGS Neutron Research Group, it is the ENRG, and I have been at RGS for the last 4.5 years. And this is collaborating with Fermilab, NOVA experiments. We are an official collaborator of the NOVA, NE, Dune experiment at Fermilab, and also EOS at UC Berkeley, the hybrid detector. And also I am still affiliated to CMS CERN experiment through the University of Iowa affiliation. And the TEA is just a design idea now. It's a huge detector, actually. I'm in the collaboration. We just wrote a proposal to the DOE, but of course we ask so much money. It's about $300 million. We don't know yet if they're gonna fund after the new president. So lots of going over there. So the first experiment actually is the NE, which I have been the run coordinator and also the project manager of NE at Fermilab. NE, it's a 26-ton gadolinium-loaded water Cherenkov detector. It is only 10 meters underground on the beam of the, like BMB at Fermilab, because I said we have 2 beam lines actually. One of them is the booster neutrino beam line, 700 MeV at the peak energy, neutrinos we see. We would like to study the neutrons coming from the neutrino interaction. So this is really interesting. Like 2, like chargeless particles, but even if the really big experiments actually is having real hard time to study neutrons coming from the neutrino interactions. We can, I mean, those experiments are so good studying, like the protons, electrons, the muons actually, because they are all the charged particles coming from the neutrino interactions. Even the Super Kamiokande in Japan, or the NOVA experiment at Fermilab, for example. But then if you want to study the neutrons coming from the interactions, like the neutrino interactions, then you should design a specific experiment for that. So how? Adding gadolinium inside the detector, because the gadolinium is having one of the highest cross-section of the neutron capture level, actually. So then a kind of, we have the gadolinium, we have the lithium, for example, and we have the boron, for example. They have higher cross-sections to capture the neutrons, actually. That's what the gadolinium is doing inside this tank, actually. But it is, of course, the homogeneous detector added with the gadolinium, like almost 0.03% of the total mass. And also, this detector, this is really important, and I just want to focus on, the detectors. The DOE at that time supported us with this experiment, with this design, for demonstrating new detection technologies. One of them is the LAPPD, Large Area Picosecond Photodetectors. I think Professor Swat came here with his PMTs. I mean, I heard that, so that's really good. And those PMTs and these LAPPDs, I'm going to compare them. So the best PMTs as of today, and I got a couple of them from Hamamatsu myself as well to build up a detector at RGS, and they have 1 nanosecond timing resolution, like which Hamamatsu is doing, like producing as an 8-inch, 6-inch, 10-inch PMTs actually, photomultiplier tubes. But then the LAPPDs, they have timing resolution in the picosecond level actually. So then almost 30-40 picosecond we are able to capture the photons as a photodetector actually. So then we have been kind of like focusing on the detector development at Fermilab for this experiment. Now we have 5 LAPPDs. They have been characterized. We put them inside the NE, so we have been working with them. And also the neutron tagging in GD loaded water. This was the first experiment did this, and after us, Super Kamiokande added gadolinium actually to the detector to be able to capture the neutrons coming from the neutrino interactions. And also the water-based liquid scintillator, which is a hybrid detector. I'm just going to move a little bit faster here. We have more than 40 collaborators from 5 countries and 18 institutions. We have 5 researchers from RGS University working on NE. I'm just going to continue. And NE detector is the closest experiment to the boosted neutrino beam, which is 700 MeV. But as you can see here, actually, where actually NE covers, which is like around here, so we can study different physics actually. Quasi-elastic interaction, deep inelastic interaction, resonance interaction. We cannot really study the deep inelastic interaction, but then mostly the quasi-elastic and the resonance interactions of the neutrinos. I'm going to talk about them. So if you look at here, actually, because the neutrino oscillation experiments mostly provide us the neutrino mass hierarchy because they focus on this, leptonic CP violation, if there's any CP violation or not, or the sterile neutrinos. If we have the 4th type of the neutrino, basically, but the accurate neutrino energy reconstruction need that all the particles coming from the neutrino interaction should be perfectly detected and reconstructed actually. For example, if you have a neutrino here coming, and then interacting with the within the detector, you have so many particles, but some of them missing. So you are not able to detect them. You are not able to reconstruct their energies. So then you cannot reconstruct the energy of the, the neutrino. So that's why. So then I'm just going to continue quickly. The neutron production is so important because we would like to measure the neutrino energy reconstruction perfectly. The NOVA experiment, it's a near detector at Fermilab far detector in Minnesota, which is about 800 kilometers away, which we are studying actually oscillation. I'm just going to continue quickly. This is the LAPPD test setup. I was one of the 2 people who designed this test setup actually at Fermilab. We focus on this detector development, but it was now actually produced by a company. It's called the Income. So, but then it started, like these came out from Fermilab and Argonne National Lab, and then the company actually kind of like focus on producing the LAPPD now. We have the quantum efficiencies. I'm going to continue this, but then as you can see, these are the old ones, but still they have the timing resolution less than 60 picosecond. This is really important for the neutrino experiments. And I'm just going to continue quickly a little bit faster. And then the EOS experiment, which is a hybrid detector. As I said, for example, the NOVA experiment, it's a liquid scintillator experiment. Any experiment, it's a water Cherenkov detector, actually. I mean, two different medium, two different detector types. And of course, NOVA experiment is a lot bigger. It's a huge detector, actually. But then the N experiment is only 26-ton detector. And then this EOS experiment, which we are also part in, like at Berkeley, UC Berkeley, water-based liquid scintillator. What we are doing here at RGS now, actually, for this experiment, we are producing water-soluble quantum dots, actually, as a water-based liquid scintillator. So then we can see both this, there you go. So we can see both the scintillation, the Cherenkov, and also the scintillation light, actually. So as you can see, it's cheap because you can just fill the tank by using the water, so which makes the Cherenkov photons, but the number of photons is not enough. So then you can add some liquid scintillator homogeneously inside the detector. So then you can see lots of photons coming from the scintillation light. And there are so many studies ongoing on this. And as for the water-based neutrino detectors, these are the experiments, any which is running. The Watchman, which was planned in the UK, and I was in the collaboration, but after I moved to Turkey, they kicked me out from the collaboration, but it's not running anymore. The reason is, this is a kind of like the specific experiment in the UK to be able to detect reactor neutrinos coming from the North Korea. So, I mean, you can do the same thing actually here. If you are able to build a huge detector, okay, and then with a really low background, you can see what kind of like the reactors they are running close by overseas, and if they are doing the enrichment actually or not. So that's what they focus on. But then it's not going because the UK cut the budget off on this one. But then the TEA, which is going to be a huge detector, water-based liquid scintillator. It is mostly water, pure water, but then we are just going to add some liquid scintillator actually inside. So then that's also, I mean, just the proposal was submitted. The Dune experiment, I'm almost done. The Dune experiment with the near detector is going to be at Fermilab. The far detector is going to be under the Sanford Underground Research Facility. This is one of the, one of the old mines. But then it's almost 800 miles away. But this is just going to have a 70 kiloton liquid argon, actually. So the budget is almost $4 billion for this experiment. It's building. So they already built the cavern here and this cavern. Now actually they are building the accelerator here and also the neutrino beam line. And then they are just going to start building the near detector at Fermilab and also the far detector in South Dakota. And so this is one of the, huge experiments in, is going to be really, is going to do a lot of physics studies actually for neutrinos in the coming years. This is really important. And then the other ones, I just want to mention them. One of them is the Hyper-K. Hyper-K experiment. It is also accelerator neutrinos coming from the J-Park, the accelerator in Japan, which is about like 300 kilometers away. 40,000 Hamamatsu 20 HPMTs. They use 26,000 tons of target pure water, actually. They are planning to run in 2028 or 2029. Juno experiment in China. So they are going to detect reactor neutrinos coming from different power plants, actually. One of them is the Yangjian and others the Taishan or whatever they call, 53 kilometers away. And also they would like to focus on different types of neutrinos by using this experiment. It is 20,000 ton liquid scintillator. And as you can see, the difference, main difference, one of them is a water Cherenkov detector, another is a liquid scintillator detector. One of them is focused on the accelerator neutrinos, another is mostly focusing on the reactor neutrinos, for example. But both of them would like to study the oscillation parameters, actually, and they would like to understand the mass of each neutrino types. That's what they want to do. And this is, my slides are done here, but I just want to mention, if I have time, maybe like 1 or 2 minutes, I just want to mention what we can do in Turkey. Okay, so this is really important actually for the neutrino studies. Of course, we have different groups. They are focusing on like different, like atmospheric neutrinos, maybe supernovae or whatever actually. But then, what I am interested in, when I was at Fermilab, I started doing like this research. We have 3 power plants were planned in the past, but one of them is the Mersin Akkuyu nuclear power plant under construction. The Sinop, I believe it's on hold. And then the other one, the Eneada, not sure what happened for that one. I think it didn't really start. But these reactors actually might be really good reactor neutrino study startups in Turkey. So because we have a really low background. I mean, we don't have so many reactors around. So in Europe, actually, that's one of the main problems. In France, for example, they have so many reactors around, and then they have so many different backgrounds actually coming from different reactors. Yes, also, yes. I mean, hopefully, like, I don't know when, but that would be really, really nice, of course. Perfect. It's a really good news. Mm-hmm. Perfect. I mean, we should talk on this definitely. So that's really good. And then what we did with my colleague, actually Vincent, at Fermilab. So we studied. I mean, we did all the feasibility studies, and then we did a kind of like the simulation studies actually. And if we can see any reactor neutrinos coming from the Mersin Akkuyu actually, and then if we are able to build a 30-ton detector 1 to 2 kilometers away from Akkuyu nuclear power plant, which is going to be outside of the campus, so that's really safe. It's mostly the physics studies actually. We just want to focus on this. And then we are able to see 200 neutrinos per day at 1 kilometer distance. And after the background selection, but then this is a really careful selection, almost 50 neutrinos can be observed actually from the simulator results, and it was published. And then what we came up with this, and I told my students, some of them are here actually, they have been working on this. I said, why don't we build a 1-ton detector at RGS? And then we can start with the cosmic detector studies. And then later, if they are able to let us, maybe we can just take this detector again as a kind of like a compatible, this is a kind of like, we can move it actually. I mean, it is, and as you can see, it's on wheels. We can move all the electronics, that's fine. If they let us to get in the campus of the Akkuyu nuclear power plant, outside of the building, I mean, we don't want to get inside the building, of course, but outside the building, at the 100, like 50 to 100 meter from the nuclear reactor, we see also really good amount of neutrinos by using a 1-ton detector. So which is running, by the way, but what we are doing with this detector at RGS now, we are continuously taking cosmic data now, and we have high quantum efficiency, high timing resolution PMPs around, and also gadolinium loaded, this one. And also we are studying the neutrons coming from the americium beryllium source. So we lower the americium beryllium on top, and then we are just studying a kind of like how these neutrons are captured by the gadolinium. And then if we can see a kind of like the symmetric capturing or the primary, secondary neutron separation. Actually. That's all. Thank you so much. Yes, definitely. Very early, like very early in Big Bang era. So I think for those ones, The first thing, we cannot detect them by using the Cherenkov detectors. Because of the threshold of the Cherenkovs. We can detect them by using the liquid scintillators, and those like the Elgin, really high efficiency scintillators actually. But the problem is to be able to detect them. If you are able to, build a 1 kiloton detector, it's not possible to see them actually. That's one of the reasons why we need to build a huge detectors. To be able to build the huge detectors, massive detectors, when I meant the huge, and also really high timing resolution detectors, like photo detectors, for example. That's why these LAPPDs are so important. But then we should kind of like move from nanosecond level timing resolution to the picosecond, like maybe 1 picosecond timing resolution level. To be able to detect them inside the massive detectors. The second thing, their quantum efficiencies. The PMTs have quantum efficiencies almost 40% now. So which means that 40% of the photons hitting to the photocathode are knocking out the electrons, the photoelectrons. The LAPPDs have almost the same level, almost like 38, 40%, 41, 42%. But we should be able to also get higher, quantum efficiency photodetectors as well. Yeah, half of them, yes, definitely. And also, like as for the timing, it's not easy to detect them because, for example, if pion is decaying, if you are able to see two photons, separate the two photons from each other, the timing resolution should be around 10 to 20 picosecond level. But we detect them really late, actually, like afterwards, after, like they come up. They travel after some time. Yeah, definitely. No, okay. So this is what they told the microboon experiment at Fermilab. They said this. They have been searching all the neutrino flavors, okay, and then they are a kind of like trying to like put the limits, like for the rest of the like inside their background, of course. Because we have a huge background for the neutrino studies. They are a kind of like the reconstructing the electron neutrino, reconstructing muon neutrino, reconstructing the tau neutrino, and to be able to reconstruct the energy of each of them, actually, they should study the physics backgrounds. Okay, by a kind of like digging the physics background, they are telling us we are able to, like the neutrino, like that's really interesting. Like we are able to reconstruct only three flavors. We don't have any neutrino like thing inside the background. Actually, that's what they told us. Uh-huh. Because their experiments, I can say it's a liquid, it's an argon detector, actually, by the way, the microphone experiment. Sorry, liquid scintillator experiment, microphone. But their experiment is not sensitive. But still, they are telling us, like we are searching if there is anything actually here. So it's not really sensitive. So what is going to be sensitive in the future? The dune, most likely, because it's going to be almost 2,000 kilometers under the ground, 70,000 liquid argon detector. So then you can see so many different backgrounds as well. Yeah. Well, they are building. This is the only thing DOE didn't cut the budget off. This is, I don't know, but uh, I hope Trump doesn't hear it. So this is really interesting. Yeah, please. Sorry. Yep. Mhm. Definitely, we can do it actually. So what we have, for example, these detectors, each of them, we have trigger systems. So the trigger is a kind of telling the detector what's coming from the accelerator. That's why we focus on the accelerator neutrinos. We are able to trigger the beam itself. But also inside the detector, each detector actually is designed to be able to see electrons, for example, the muons. If they have enough energies, each of them is just going to be, I mean, if the electron and the muon higher than the Cherenkov threshold, they're just going to generate the Cherenkov photons. But then the rings are different actually. Those are a kind of, like the conic shape of the photons. But then the rings, one of them is larger, another is smaller. One of them is foggy, another is really clear actually. We are differentiate, I mean, we are able to separate the subatomic particles coming from those neutrino interactions. So then we should be able to, because the beam at Fermilab for NOVA experiments, when we say the muon neutrino, it's mostly muon neutrino. For example, 96% of the beam is muon neutrinos. The rest, 4%, is mixed of the electron and the tau neutrinos. Studying the taus are hard because they decay so early. I mean, in a really short lifetime they have. But then the electron neutrinos we are able to study in the experiments. Yep. Yes, definitely. Yes. Uh-huh. For the ice cube, for the supernova, I don't know. But then there is one thing I know. And also inside this trigger system, I think Snooze or I don't know, like because they have a trigger system when there's a supernova explosion, actually. We also take the same trigger for nova. And around the globe, actually, I can say all the experiments are using the same trigger system. And IceCube is one of the experiments. Is a kind of like up, like keep this running up the trigger system. But I don't know, maybe like people. Mhm. Really high energetic neutrinos, actually. Yeah. Uh-huh. Yeah. Because what we do, mhm, what we do, like in our nova experiments, whenever they kind of like publish, but in really quick, because trigger these experiments are controlled and run by 24 hours actually. We have one of the like remote operating centers at RGS which we built now. We are controlling the any experiment 8 hour shift, for example, and then our shifter is controlling the experiment and watching everything actually. They cannot really leave the computer unattended, so that they should just watch what's going on. When the trigger comes for the supernova explosion, NOVA experiment is focusing on the data. If there is anything actually we can see beyond what we have been measuring actually. But I mean, so far we haven't seen anything because even those specific experiments really didn't see like lots of things. Thank you. Mhm. So definitely. So then here, the color bands are defining, like by using those eigenstates, which neutrinos. Like for example, the blue is a kind of the electron neutrino. The like the other one, the fraction of the muon neutrino. Other one is the fraction of the purple one is the tau neutrino. The mass hierarchy is the mass of each neutrino. For example, the electron mass. Like as you can see, for example, this is the blue. But then the electron mass can be defined by nu1, nu2, and nu3 actually. This is a kind of like eigenstates of these three, like, like these are the eigenstates, so that it's the fraction here, another fraction here, another fraction here. So then the normal versus the inverted hierarchy problem is this. We know in between these two, because as you can see here, for example, delta M 21 square actually was calculated as, these are the experimental results by the way, and as the 7.50 plus 0.19 minus 0.17, that's the total uncertainty on them, times 10 to the negative 5 EV square actually, for example. This is already calculated by using the experimental results. NOVA has been calculating this. T2K experiment has been calculating this actually. And I can say one of our recent studies with T2K, it's a combination of the data, combination of the results was published in Nature. And I was part of that study during my postdoc, and then later on we continued. But here, if you know the delta M 21 square actually, experimentally, but if you don't know this, so then either this normal hierarchy is going to be nu one, this is the mass level, nu one, nu 3 larger than nu 2 larger than nu 1, or it's going to be nu 2 larger than nu 1. It is the same here, as you can see, but there it's going to be larger than nu 3. The problem here is the mass hierarchy eigenstate of the nu 3 in terms of, or by comparison of the nu 1 and nu 2 actually. If we have more data and to be able to detect the tau neutrino decays, and then tau neutrino the oscillations actually, then we should also be able to detect, like the delta M 32 square actually, experimentally. So then if we have the experimental results for the tau neutrino oscillations, better experimental results, then this problem can be solved. Yeah, superposition states. Yes, that's perfect. Yes, that's good. I mean, superposition of those like 3 eigenstates. Yes. Mm-hmm. Well, there are a couple of things actually. One of them is we measure. There is a probability function first. I mean, the probability function is telling us, like that in the theoretical model, how many muon neutrinos are gonna oscillate to the electron neutrinos. Okay, then inside that probability calculation, you have a near detector here, far detector here, and experimentally you take, like the number of muon neutrinos here and the number of muon neutrinos here. You take number of electron neutrinos, number of electron neutrinos, and then make the calculations on the statistical base and how many muon and electron neutrinos are oscillating to each other. Then we can calculate actually. That's one of them, of course. Yep. Yes, absolutely. Avalanche photodiodes, I believe you mentioned the APDs. The avalanche photodiodes actually have been using for NOVA experiments because we have the PVC, like we have the long PVCs filled with the liquid scintillator. Inside there's an optical fiber. So the optical fiber is a kind of like getting all the photons, and then you are able to get the photons out by using the optical fibers. Those optical fibers actually are attached to the APDs for the NOVA experiments. But yes, absolutely. But they are cooled down actually for the Nova. Yes, absolutely. Uh, but then those ones, and I think Maryland College Park. We have a couple of professors. They have been studying these for the CERN experiments, like the CMS or the Atlas experiment, like superconducting nanowires. And but then these experiments, like one of the biggest problems is this. Let me just show this. It's like, okay, there you go. For example, this one is a really small, tiny. but even like we can just go the bigger ones. Okay, this one. This one is 20,000 ton liquid scintillator. They are equipped with 15,000 20-inch PMTs and 25,600 3-inch PMTs. So, and also the cost base, I believe, if you are able to cover a huge areas by using the superconducting, like the wires, for example, and it's not really feasible. Yeah, because each of them, like these 20-inch PMTs, Hamamatsu, high quantum efficiency, high timing, like 1 nanosecond resolution, 1 to 2 nanosecond resolution, and almost like 40% quantum efficiency PMTs, these ones. But the 20-inch is a huge, like 50 centimeter detector, you know, like the diameter. But then each of them is about like $45,000. To be able to reach them like by using the other technologies, it's not really easy. So that's the reason. I mean, the massive detectors, you need the photo coverage actually should be perfect. So that's why these EOS experiments, even this is like the photon detector, but as you can see, the photo coverage is perfect because each detector is so close to each other. I mean, this is really important, the photo coverage as well, because you don't want to miss the photons coming from in between the PMT. So you would like to increase the photo coverage. Okay, thank you so much.